Okay, good morning or good afternoon everybody, and welcome to this webinar from Precision Polymer Engineering and Global Spec, and thanks for taking the time to join us today. Under the title Precision Polymer Engineering, you'll see our subheading that says Advanced Sealing Solutions for Critical Applications. Fundamentally, our products are based around elastomer materials, which of course have many applications in ensuring good vacuum is maintained, or in liquid applications to contain the media. Although we have in excess of 150 different materials that we provide into the semiconductor sector alone, we primarily concentrate on those applications and processes that can have a real impact in your cost of consumables or product yield. So in today's presentation, entitled O-Ring Seals, How Do You Choose the Right Materials?, I will be focusing more on dry, or the more common plasma processing applications, and the effect of various process chemistries on a wide variety of different elastomer materials. Okay, the other thing I'd just like to do before we get going is introduce myself and give you some details about my background. So my name's Knut Beekman, and I'm the Global Marketing Manager for Precision Polymer Engineering's Semiconductor Products and Materials. As far as my background goes, my semiconductor experience has essentially been accumulated through about 30 years working within the semiconductor equipment manufacturing industry, where I've worked in several technical and latterly more commercial roles, but starting out as a process engineer and more specifically within technologies such as plasma deposition, plasma etch, and physical vapor deposition, but I'm also generally familiar with most of the other technologies used to manufacture semiconductor devices. Okay, so this is a quick overview of my talk today. For those of you who've never heard of Precision Polymer Engineering, I thought it would be good to just give you a couple of slides with some background to the company, who we are, where we are, and some of the more relevant capabilities of PPE. The presentation overall delves into elastomer compatibility with process chemistries, but I think it would be useful to go over the background, so I have a slide which describes our motivation and why we decided to do this work, which by the way is also actually still ongoing. So in order to also put this into perspective a little bit, I'm going to describe the basics of what can go into an elastomer, and more specifically the elements that are relevant for materials developed for semiconductor applications. Then we'll start to get into how we've carried out the material testing and taking a quick look at both the hardware we've used and the various different chemical environments to which we've subjected our test materials. So then I guess comes the real meat of the presentation, where I'll show the results of how our test materials performed, and I'll follow up with some observations and conclusions. Okay, I'll start with a brief overview of Precision Polymer Engineering, or PPE for short. We've been around for a while, and we're currently celebrating our 40th year this year, and we've seen pretty good growth during that time. Now we focus on market sectors such as oil and gas, heavy equipment, as well as the semiconductor industry. We're based in Blackburn, which is in the northwest of England, where we have about a 75,000 square foot facility for production, and we have various accreditations for manufacturing processes and quality, etc. As well as manufacturing operations, also based within the same facility are our application engineering and research and development teams, as well as sales, customer support, and various administrative functions, and this is quite useful as it maintains good communication between departments. PPE was acquired by IDEX Corporation in 2010 and therefore became part of a much larger organisation made up of over 80 subsidiaries, and IDEX Group has a total revenue of over $2 billion. This obviously gives PPE certain advantages, including significant financial security that comes with being part of a much more diversified group, and also it gives us access to much greater investment capital than PPE would have as an individual entity. As you can see by the two images in this slide, that investment has recently been put to good use through an expansion of our facility in Blackburn to another manufacturing site in Brenham in Texas, which is currently serving oil and gas customers and will shortly also be able to support semiconductor customers in the USA and other regions around the Americas, and both these sites specialize in compression molding. We also recently acquired another company based in Italy called Novatima, who also produce elastomer products, although they concentrate on much higher volume applications with custom injection molding capability. Okay, you can see from this image that PPE also has a global presence across the major regions of America, Asia and Europe. Our headquarters are in the UK, in Blackburn, with the now 3 manufacturing sites in the UK and Italy and USA. We then have sales that operate across the various regions, either through our direct sales teams or a distributor or dealer network. And we also have applications engineering and materials resource in the USA, as well as those based in the UK. So we're well represented, particularly across the major semiconductor manufacturing centres globally. So quite a large part of the PPE value proposition, as well as the unique elastomer materials we provide, is the material characterization resource. We have a highly qualified team of technologists and chemical engineers who are available for technical support and are able to advise on appropriate choices of materials for specific existing or potential new applications. As you can see from the analytical equipment and test equipment list, we're very well equipped for material development, evaluation and characterization. So these techniques such as FTIR, TGA, etc. allow us to do things like identify the material bond structure, measure thermal properties including coefficient of thermal expansion, obtain compositional information, and we also have a vacuum plasma process tool which enables us to look into O-ring degradation versus plasma exposure. So currently this tool is limited to non-toxic type of chemistries, but therefore we can do oxygen plasma resistance evaluations internally, and that's still very useful as it's still one of the more aggressive media for an O-ring or elastomer material. I mentioned our manufacturing expansion into Texas, and we also already have an additional technical lab in Houston that has a similar list of equipment for material characterization. Okay, as I'm sure we're all aware, semiconductor manufacturing can be a bit of a risky business. So why is that? Well, although I may be stating the obvious, let me just substantiate that statement a little bit. So chips are made on substrates or wafers, and there are many multiples of chips on each wafer, which is especially true for larger wafer sizes, and that's obviously one of the main benefits in keeping costs down by processing a lot of products at the same time. Then wafers are also processed in batches of usually 25 wafers. Fast throughput is always a key equipment requirement, and that throughput needs to be as high as possible to make maximum use of the expensive fab space and resources. So we have lots of products that are processed simultaneously, and it's all progressing through the fab at a relatively fast rate. All good when you consider there could be easily upwards of 1,000 individual process steps to make the product. Now then, equipment providers have a lot of inbuilt monitoring of the critical process parameters and also various parameter feedbacks to monitor the tool. And all this data is logged in real time to ensure the equipment is functioning correctly. Good examples of this would be gas flows, pressures, powers, and various plasma feedback parameters. Again, all good stuff. However, during processing, all parts of the chamber internals are exposed to whatever chemistry is going on, and that obviously includes any seals or O-rings. The wafer sits in the chamber, and therefore anything in contact with the chemistry and in proximity of the wafer, again, including seals and O-rings, becomes a critical component, which is capable of contaminating the wafer. Now that contamination could be something obvious, such as a particle, or it could be something that has the capability of altering the electrical parameters of the device, or whatever product's being produced. These are also the sort of things that are either difficult or impossible to monitor in situ. And this means that multiple process passes can happen before anyone realizes something has potentially gone wrong. Another factor to be considered is that some of the effects of the contaminant may be immediately catastrophic and therefore easy to spot. But in other cases, some categories of contaminant might create a latent defect which only becomes apparent after the part has shipped. So here I'm thinking of metallic ion contamination, where the effect on the device also depends on the type of metallic component, such as whether it's sodium or copper or some other metallic element. The other key factor is lifetime of chamber components and how often parts need to be cleaned or exchanged, which is fundamentally determined by the erosion rate. So we now begin to understand that any change in materials used in a process chamber or critical location has some risk associated with it. While some fabs have the capability and resources to test and evaluate new materials, that doesn't apply to all fabs. So how to decide what's a good change that might save cost and what's a bad change that will potentially have the opposite effect? It's not unusual for elastomer manufacturers to provide data on erosion rate of materials. PPE has done this in the past, and it's published in our PERLAS brochure, and other elastomer providers do much the same. In reality, however, overall this data is quite limited. It generally shows only 1 or 2 homegrown materials being compared against 1 or 2 other products that may or may not be in the same category of materials, and that's invariably not clear from the published data. Often, plasma lifetime, or more precisely erosion rate data, is also not the whole story. After all, the elastomer will ultimately be eroding, and whatever byproducts or constituents are released during the process will be happening from process number 1 all the way through to the PM or clean cycle. So during this study, we've tried to capture a far greater variety of products, not only internal materials but also other materials from the leading elastomer manufacturers. In this way, we hope to be able to make a more informed choice about material recommendations to end users and equipment manufacturers alike. We'll also be using this data to fundamentally drive our new material development and go through a much more rigorous testing process before release and launch of new products. Okay, let's just take a step back and have a quick look at Elastomer Basics and what raw materials we have at our disposal to make an O-ring or a seal. So we have our basic polymer chains, but unless we connect them together, if we were going to apply a force to such an unconnected material that was just a simple collection of polymer chains, these chains would just effectively slip and slide across each other, and then when the force is removed, they would remain in this, let's call it, slipped configuration. This would be a typical scenario for plastic materials, but that's really not what we want here if we want to create a sealing force, which is what we need. In order to make connections between polymer chains, a so-called cross-linking agent is used, and this then becomes a part of the final structure. And in order to make this happen, we need a catalyst, and this helps to get the cross-linking reaction to start. Plus, we add a bit of heat, a bit of pressure during the molding process. So the overall process of linking our polymer chains together means that when you now come to apply a force that either stretches or, more importantly, compresses the material, we've created an elastic material that exerts a sealing force, and when that external force is released, the elastomer will, in theory, recover to its original shape or form. So we've created a material that is elastic. However, we still need to be able to adjust the properties of our sealing material depending on application, and we achieve this through a rubber compounding process. Here you can see an array of various different materials or groups of materials that can be used in rubber compounding in order to adjust the final properties of the elastomer or to adjust the way the elastomer can be processed or manufactured. Elastomers are obviously used in many different applications across different industry segments. However, many of these compounding agents may well not be suitable for semiconductor applications. So let's look at some examples. Process aids tend to be low molecular weight materials leading to volatile outgassing in vacuum or high vacuum applications. Pigments to add colour are mainly metal complex based. If you see a green O-ring, for example, it's highly likely it will have a chromium oxide based filler system. This can then be released through erosion processes over the lifetime of the seal in a process tool, although clearly this also depends on the process chemistry. The net effect in these examples is that the semiconductor process becomes uncontrolled, or even worse, the substrates can become contaminated, leading to changes in device characteristics. For semiconductor-related applications, which are really among the most stringent for any elastomer material, the aim is to try to limit to a minimum the number of ingredients, and not only that, but the ingredients are carefully selected for process compatibility. At the same time, we still try to achieve the desired elastomer properties. Most common elastomer materials that are used on process tool, or let's say in critical areas of process tools within the semiconductor industry, are those known as fluoro or perfluoroelastomers, or to give them their official material designation, FKM, fluoro, or FFKM, perfluoroelastomers. PPE provides these types of materials under various brand names such as Kimura or Perlast, Perlast specifically being uniquely FFKM materials, or we have a PPE brand which is generally an FKM material. The basic distinction between an FKM and an FFKM, apart from FFKMs being more expensive, is the amount of fluorine present in the polymer material. So I should make it clear that when we talk about FKM and FFKMs, it's the base polymer we're referring to. There's still a wide variety of available products based on these FKM and FFKMs. So we've seen that there are various basic polymers, FKMs and FFKMs, and these are often fundamental in determining the properties of the elastomer. I just want to also discuss in a little bit more detail some further additives referred to either as reinforcement systems or filler systems. If you've come across elastomers or O-rings in the past, you may have noticed that many or even most of these are black in colour. And there's a good reason why they're black, and that's because a common reinforcement additive is a material called carbon black. The clue's in the name, right? Carbon black, even in small amounts, fundamentally affects the colour. And there are again many different types of carbon black. Typically, there are around 6 that are commonly used carbon blacks for elastomers. Each one provides varying degrees of mechanical strength. Different structures reinforce the rubber in different ways. Some make elastomer processing easier, others result in very tough materials, and it's possible to mix and match to get the properties that are needed. The disadvantage is for some semiconductor applications, and as we've already alluded to, the breakdown in the higher elastomer structure results in transferable residues or particles which are undesirable, especially where the seal is in one of those critical locations in a process tool. The carbon black manufacturing process has been around a long time and is also less stringent, and impurities or contaminants are more uncontrolled. The requirements of the semiconductor industry were just not taken into account in carbon black manufacture. An alternative reinforcement system to carbon black is shown in some of the other images. Silica or silicon dioxide is often used, but again there are different types of silica materials. Silica is a naturally occurring material, however natural silicas have a number of impurities including metal oxides and other inorganic compounds, and the level of impurities are relatively uncontrolled. A better option for semiconductor applications in order to avoid metallic impurity contamination is to use synthetically manufactured silica, which has typical purity levels of greater than 99.9%. Finally, on the subject of fillers, there are also so-called organic reinforcement systems with typical filler types including PTFE and PFA. The natural extension to such fillers are then the dark arts of filler-free systems, where the polymer architecture itself can be described as self-reinforcing. PPE utilizes these types of novel technologies in several elastomers or elastomer grades. These organic filler or filler-free materials can be regarded as the purest, being entirely organic elastomer materials. The plasma resistance of these types of purely organic products is generally not as good as the inorganic filled materials or the silica-filled materials, but they have the potential advantage that the byproduct of degradation processes can be volatile and therefore doesn't lead to particle generation or particulation of the elastomer. Longevity is therefore traded off against cleanliness, but it's particularly relevant to processes at the forefront or leading edge of technology and for critical process tool locations such as chamber lid O-rings, isolation valve O-rings, slip valve door seals, or any other area that's effectively plasma wetted. Okay, so now we've got some idea of the variables that go into making O-rings or elastomers. This is where we start to get into the more practical aspects of what works or doesn't work and how we've characterized the various different elastomer materials. The work I'm presenting has primarily focused on plasma resistance of O-rings. When we hear the word plasma in the world of elastomer manufacturing, it's not often appreciated that not every plasma is the same. In PECVD processes, the plasma configurations are generally capacitively coupled, where the electrodes are parallel to each other and one, or more rarely, both electrodes are driven by an RF power supply. High-density plasma deposition, or etching, has different requirements and generally more configurations of plasma sources such as ICP, TCP, and RIE. The plasma source requirements fundamentally hinge around the relative need for control over the degrees of chemical and more physical ion-based etching, and the need for sidewall profile control. As I just mentioned, etching tends towards the use of high-density plasma sources, but we also need to take into account the common use of remote plasma sources used to clean deposition chambers. Such remote plasma sources are again high-density, inductively generated plasma designed to create active species that will react with materials coated around the vacuum chambers to which they're connected. So what we've tried to do is find equipment, or more precisely partners, that can simulate the various different sources and then also supply the chemical environments that are commonly used. Of course, individual process recipes are treated as proprietary information and generally kept as closely guarded secrets by the original equipment manufacturers and end users alike. And that's quite rightly so. A lot of time and effort goes into developing these processes, and that's fundamentally what creates the value. These processes are potentially also quite specific to a set of hardware or chamber configuration. All this makes life a little bit difficult for suppliers like us. Nonetheless, of course, we have to start somewhere, and for the purpose of these tests, it seemed reasonable to just focus around certain key or common chemistries. So the chemical environments have been chosen around common processes such as silicon, dielectric, conductor and compound semiconductor etch chemistries, as shown in the slide as processes 1 and 2. In the absence of access to a remote NF3 plasma source, which ideally we would have preferred, process 3 was chosen to simulate this kind of remote plasma highly chemical active environment. So we're using SF6 in combination with a small ICP65 plasma source, specifically chosen to be a good source of fluorine radicals, and one of the things that distinguishes radicals is that they have much longer lifetimes compared to other active species, as they have no net charge and are therefore not affected by electric fields or other charged particles. What I didn't mention actually in the last slide is that the number of samples we could run in each test is also fundamentally a function of the size of the ICP source, or with regards to the oxygen plasma test, related to the size of the upper electrode. So in processes 1 and 2, all samples were run simultaneously, and for processes 3 and 4, they were run in several batches. Temperature is also potentially an important factor. However, as we have a mixture of FKM and FFKM materials which have different temperature capabilities, all tests were done at or around 100 degrees. Okay, so we now know what plasmas and chemistries we're using. What are we going to measure, or what would we like to know? One of the key things, obviously, which would be related to the lifetime of the component is the erosion rate or mass loss. So we can't say for sure how this would relate to lifetime in an actual process tool, as the conditions of the test are still somewhat different to the real world, where the seal would normally be sat in a groove and more shielded from the elements, as it were. And as I mentioned previously, individual tool hardware and process parameters would come into play. What we can do is look at the relative erosion rates under the same conditions across multiple different materials and grades. So what we're looking at is trends and some common trends that will potentially indicate material groups that perform better or worse, and whether the same trends are true across multiple different plasma chemistries. In order to make meaningful interpretations of the erosion data, we need to know some other things about the elastomers. One of the key factors that determines the properties of the elastomer is the filler system or systems. For our own materials, we obviously know how they're compounded, but this isn't the case for all the materials that we've tested. So some of the other techniques, such as FTIR, allows us to determine the basic polymer type, for example, whether it's an FKM or an FFKM. And TGA gives us a basic understanding of the filler system that's being used, at least enough to know whether it's organic, inorganic, or without any filler at all. The test samples could be categorized in a number of different ways, but essentially we looked at a variety of elastomer flavors across multiple sources. Ultimately, we'd like to be in a position where we can make informed decisions about recommending the correct materials and minimizing the risks to the user. We also included some development materials which are essentially either changes to existing compound formulations or changes in the way they're processed or vulcanized and cured. We limited the number of base polymer options around those that we believe are most likely to be used in the more critical applications. Hence, we also had more FFKM materials on test than FKM materials. In total, though, we had about 30 different samples or materials, although not all in equal quantities. The characterization process is also still somewhat work in progress, so right now there are still a number of samples to be tested. I should probably also mention that during this phase, the samples were simply all directly exposed to the environment with no additional stress or stretch applied to them. So what we can see here is essentially various different TGA spectra for several different elastomer materials or groups of materials. So for anyone not familiar with the technique, thermogravimetric analysis allows us to monitor changes in the material as we increase the temperature at a constant rate. And when I say changes, I mean things like phase transitions or vaporization. The test is basically split, where the first part is done in an inert atmosphere and then switched to an oxygen-containing ambient at a certain temperature. And for the examples shown, the change in ambient occurs at 600 degrees C, or for those of you working Fahrenheit, that's 1112 Fahrenheit. Then the temperature continues to ramp up to 1000 C, which is 1832 Fahrenheit. The spectra in the slide and the technique generally tells us, at least at a top level, the type of filler system that's being used. In the inert ambient phase, up to 600 C, 1112 Fahrenheit, we'd normally expect the polymer to be fully degraded. The changes in profile with temperature is what we're really interested in, So if we take a closer look at the examples, the first one, top left, is fairly straightforward. It shows a smooth profile of weight against temperature and drops to 0 at around 500 C or 932 Fahrenheit. If we look at the spectrum top right, it shows a similar profile but doesn't drop to 0. There's a residual mass even after the ambient changes all the way up to 1000 degrees C, 1832 Fahrenheit, indicating an inorganic residue or inorganic filler in the compound. So then the spectrum bottom left shows a slight kink in the profile at between 440 C, 824 Fahrenheit to about 550 C, 1022 Fahrenheit before dropping off to 0 once more, and this indicates that it's got an organic filler. Then finally the last spectrum shows a similar kink and a small residual mass, indicating a bit of a hybrid material with both organic and a small amount of inorganic filler. Okay, over the next 5 or 6 slides we'll see how the various different materials perform in the different plasmas and plasma chemistries. And here we're looking at the relative performance in the chlorine-based chemistry. So chlorine is commonly used for etching metals and also compound semiconductors, and can also be used for silicon etching. You may notice that there is also HBr in the mix, and in case you're wondering why is there HBr, it's often used to increase selectivity either to the mask or, if it's a polyetch, to increase selectivity to silicon oxide. Okay, so we can see all the various different materials along the x-axis and the percentage mass loss against the y-axis. Total process time and hence exposure time was 14 hours. The bars are all color-coded as to whether the material is a PPE product or another grade. In each of the following charts I've added a label to the data point which indicates whether the material is an FKM or an FFKM. You may also notice a label that states HPE, which stands for High Performance Elastomer, and this is a PPE product which uses a proprietary self-reinforcing polymer structure. The labels are also color-coded, and the color indicates the filler system used based on the TGA data as previously discussed. So, okay, if we look at the color of the labels, and let's just look at some of the headlines, and we see there's a bit of a blue bias going on in that these tend to be the better performing materials with lower weight loss. Blue indicates an inorganic filler system, so it looks like inorganic filler systems are generally better than organic filler systems, or also the filler-free materials as indicated by a green label. There are a couple of other interesting points. Somewhat unexpectedly, the top performing materials are not entirely made up of FFKM polymers. The lowest weight loss material was actually an FKM, admittedly inorganic filled, but there were also some organic materials that performed well, and in particular an organic filled FKM grade was also in the mix. The other data point that I'd like to draw attention to is that one of the development materials that's a filler-free grade performed quite well and also got in amongst the performance of some of the inorganic materials. You may notice one of the labels has an asterisk, and that's a material that we initially thought was a purely organic filled compound, but following various repeats of the TGA analysis, which all indicated a consistent but small amount of residue, leading us to the conclusion that it's mainly an organic filler with a very small amount of inorganic filler in the compound. So in this slide we're looking at the weight loss results for the SF6 with oxygen process. Fluorine-type chemistries with oxygen are typically used for dielectric etch or also silicon etch processes. There may be other fluorine-based gases incorporating carbon, such as CHF3, C3F8, etc. But some of these gases can be more or less polymer forming, which fundamentally depends on the fluorine to carbon ratio. So there was some concern when we were setting up these tests and deciding on the chemistry to use whether a polymer forming element would potentially affect the sample erosion test. Oxygen can be used to increase the fluorine to carbon ratio, so the SF6 oxygen chemistry was chosen to eliminate any chances of process polymer formation, and as oxygen is quite a key factor in elastomer degradation, this was also added to the mix. So if we look at the data, you may start to notice that a pattern is beginning to form. The same color coding applies to the data labels as before, and we can see again that the better performing grades are the blue labels or inorganic filled materials. And in this chart there looks to be a clearer distinction between inorganic materials, organic filled grades, and then the ones with the highest erosion rate being a cluster of the filler-free materials on the left. Notable exception again is one of the development grades of filler-free material, which in this case doesn't get into the performance level of any of the inorganic filled grades, but was actually a strong contender amongst the organic filled grades. So now we come to the plasma erosion test that was designed to simulate the remote chamber clean processing that's common to many CVD type process systems. So we're looking at the material resistance to SF6, but in a plasma source configuration that is a good source of fluorine radicals. Whereas in the previous two plasmas and chemistries, I think there was a clearer distinction between erosion rates and filler types. This test has yielded a bit of a mixed bag of results. Okay, so the best materials are a carbon black filled and again a couple of inorganic filled materials. Thereafter it becomes a bit blurred with some organic filled grades in the mix with inorganic filled materials. Generally the filler-free materials are again towards the high erosion rate end of the spectrum, but not this time the worst performers. But again, as we've seen previously, one of the filler-free development grades outperforms the other filler-free materials and is in the mix of medium performance grades. Okay, and a quick note about the grades at the far left of the chart, which are Kimura K13X and Nanofluor Y75N. Whilst they're definitely in the not to be recommended category for a remote plasma type process, these grades performed reasonably well in the previous SF6 with O2 and actually were amongst the top performers in the chlorinated chemistry. So we start to also understand very well that we're seeing some key differences of material compatibility with process chemistry, and there doesn't necessarily seem to be one material that's performing across all processes. Okay, so now we're on to the oxygen plasma resistance of our test materials. Oxygen is really the main constituent of resist strip or ashing processes, and in reality one of the most aggressive environments for any elastomer. Okay, so firstly, apologies that this chart admittedly has a lot of information on it and it's a bit difficult to read in view of all the data points and the font size is a bit small. So if you're struggling to read it, don't worry too much at this stage, all become clearer. Again, we're looking at worst performing materials on the left to best performing materials on the right. Generally, it seems that the data looks like it can be subdivided into three sections. We have similarly performing high erosion rate materials on the left, a group of low erosion rate materials on the right, and then a group of medium performing materials in the center section. Now, I'm sure at this point you can probably start to guess which groups of materials might be in which section. So for this chart, I've divided the data into these groups, or to be more precise, into two groups, and I'll be showing them over the next two slides. Right, so the first group is from the previous right-hand section on the previous slide, and quite simply, all those with, yes, you've probably guessed, an inorganic filler system. From one end to the other end of the chart, however, there are actually quite some big differences across materials within this group of inorganic filler systems. So the worst material has an erosion rate that's actually about 5 times higher than those of the best materials. And again, it looks like there is actually an FKM which shows fairly reasonable performance and able to mix it with the better performing FFKM materials. So we can conclude that it's not necessarily the case that all FKMs with inorganic filler are going to be worse than FFKMs with similar filler systems. So now we don't know the detailed filler systems in all the grades, and there can well be combinations of different filler systems used. However, we can conclude that not all fillers are created equal when it comes to resisting oxygen plasma degradation, and the material that came out best in this trial is actually another development grade and uses a nanofiller material that has been carefully compounded to improve the dispersion of that filler. Okay, so what about the second group from the oxygen plasma test samples, which is a combination of all the organic materials, either be they filler-free or have an organic filler system. The two best materials from this group happen to be carbon black filled materials, okay, but semicon for critical applications, we don't really like carbon black for reasons that we've gone into previously. The other end of the spectrum is again populated by the filler-free materials, albeit with a few organically filled materials interspersed. Although again with one notable exception of that same development filler-free grade that we observed in previous tests. We also see the HPE and a few organic FKMs performing quite well and able to give the FFKMs a good run for their money in this organic category of materials. So that was all the plasma data reviewed, and what we also looked at was if there were any other changes we could see from TGA or FTIR analysis from before the plasma to after exposure, to give us maybe some understanding of what may be going on during the erosion process. The good news is I'm not actually going to go through every single material comparing before and after for all the analysis, and there are a couple of good reasons for that. In this example of TGA, I'm simply showing a couple of TGA plots before and after oxygen plasma for two different groups of materials. These are fairly typical of the results regardless of material and plasma chemistry, and it's even quite hard to see from these plots, but the changes, if any, are really within the repeatability of the analysis technique. So we've concluded that this doesn't really tell us anything apart from if there are changes taking place, this technique just isn't really sensitive enough. So now we come to the FTIR data. An FTIR basically looks at the bond structures that are present. Different chemical bonds vibrate at different frequencies, and therefore when they're exposed to a spectrum of different wavelengths, they can absorb some of those wavelengths, resulting in the kind of plots that you can see in this slide. So what I'm showing here is two plots of a couple of materials before and after exposure to the SF6 radical-based plasma, and the resultant spectra have been overlaid to look for differences. And again, we're struggling to see any changes for this particular experimental group, although with a caveat that this is also still work in progress and not all the materials have been analysed yet. If we look at the FTIR spectra of the materials that have been exposed to the chlorine-based plasma, it's clear to see that there are some significant changes that are going on, and some of those are immediately obvious. So the green curve is before exposure and the red curve after exposure. So again, this is currently work in progress and we haven't assessed all the materials yet, but I'm showing a couple of examples here that are inorganic filled with completely different filler systems, and we can see some common changes occurring in similar regions of the spectrum. I'm not going to go into any further detail at this stage, but this could form the basis of a future update once our materials team have fully analysed the data. So that's another good reason not to show every single data plot that we have obtained so far, apart from the time it would take. Okay, we're getting close to the end, and again we have lots of SEM images of elastomers from before and after plasma exposure, which is also still work in progress, and I'm not going to go through every single one. But these examples nicely illustrate some of the key differences between the material groups and what might influence your choice of material for a particular application. So I've split them into inorganic filler, organic filler, and filler-free material groups. And I've selected a few different materials that show even within the individual filler material groups, there are still variations to be seen. All these examples come from the oxygen plasma tests, which overall was the most aggressive environment, showing on average marginally higher erosion rates than the SF6 and oxygen plasma test. So if we look at the inorganic filler examples across the top, the resulting surfaces range from showing quite distinct filler material with a range of filler particle sizes distributed within and on or at the surface, to quite a rough, more granular appearance and variations in the coarseness of that granularity. The organic materials equally show different behaviours, in some cases relatively smooth surfaces with a range of what look like elongated and distinct surface features, to coarse roughness and relatively large etched features to a fairly smooth morphology. Even the filler-free materials show some big variations in surface morphology, with obvious potential to create particle contamination to a greater or lesser extent. So clearly, filler-free materials may not be completely particle-free. Right, so we've seen all that good plasma erosion data and the relative performance of the different materials. We've just seen what elastomers can look like after they've been directly exposed to these plasma environments, which all tells us that small amounts of elastomer compounds in critical tool locations, such as, but not limited to, chamber lids and analysis port locations. So these bits of elastomer are going to end up drifting around the process chamber and potentially landing or condensing on the surface of the wafer. And furthermore, they can be undergoing further collisions with energetic particles in the plasma, which may create ionic contaminants. So there's a finite probability that bits of O-ring in some way, shape or form will land on a wafer. So one of the worst contaminants that the wafer can be exposed to is sodium. And then there are a whole host of other nasty yield-impacting metals that should be avoided. So on this slide, you can see we took a cross-section of various elastomer materials and had them analysed by vapor phase decomposition inductively coupled plasma mass spectroscopy, VPD ICP-MS. Bit of a mouthful. But it's a very sensitive technique yielding levels of trace metal contamination down to parts per billion. So contamination level on the y-axis and material along the bottom x-axis. The red line is a specification of one of the OEMs for critical chamber parts. One of the other things to note, so the first thing to note in particular is the y-axis scale, which in this case is a log scale. I'm sure most of you will know that a bar on this scale that's half as big as another doesn't mean it has half the amount of PPB contaminants. Each division is an order of magnitude, or a factor of 10. So the top two pearlescent materials at the far right of the chart are already about an order of magnitude, or factor of 10, better than the next material. So the other thing to note is that this is really where the organic materials get their own back for the thrashing that they got through most of the plasma erosion tests. We see that the best material grades are exclusively the organic materials, and the inorganic materials are again getting on for around an order of magnitude dirtier than even the worst of the tested organic filled grades. Okay, so what have we learned apart from the obvious that inorganic materials tend to be the best performing in plasma environments? Well, there's one filler-free material that gives us hope that there may be an elastomer process out there that can compete with the best. A couple of organic elastomers, Chimera K13X and NanoFluor Y75N, was a good example of how they perform admirably in a chlorine-based chemistry, but we have to be honest and say that they wouldn't be the material of choice when it comes to remote plasma cleaning applications, and their performance for this application is really at the opposite end of the spectrum compared with the chlorine chemistry. So I guess what we're saying is one size doesn't fit all. There's no single wonder material that outperforms every other material in every chemistry. I guess we didn't really expect this, but clearly a good pointer for development of new materials, and that it's important to focus. The other positive from this is that we're also getting better and we're better positioned to make material recommendations. We now have much more information available to make those informed decisions. If your application and/or device demands the cleanest material when it comes to trace metal contamination, and if the example specification is anything to go by, the choices are actually quite limited. As a manufacturer, we're seeing a greater pull from the industry for cleaner and filler-free materials. Right now that means a compromise in lifetime, but based on our SEM analysis and on the one development material, not all unfilled grades are created equal. And of course I should mention that at the end of the day the choice of elastomer comes down to a number of factors, and many that we haven't actually discussed today, such as, for example, temperature capability and, depending on application, potentially also mechanical properties, etc. Okay, just before we finish, I would like to draw your attention to the PPE website. It's segmented by market sectors, and it's fairly easy to navigate to the semiconductor section. Here you'll find some very useful information about the range of PPE materials, including product brochures and material data sheets, specific applications and chemical compatibilities. So in order to gain access to these sections within the website and all this useful information, just requires a simple registration to set up a username and password, and you're in.